Welcome everybody to our session. We got a lot to talk about here today, so we're going to get rolling real quick. This is path tracing of Nanite in NVIDIA's Zorah demo that you probably saw from our CES launch announcements. I'm Evan Hart. I'm going to just kind of give you some background, some overview today. All three of us worked on this project, but Jayan, Adam had much more interesting things to talk about, so they're going to give the majority of the presentation. What are we going to talk about? Well, I'm going to give you the intro. We're going to talk about path trace light transport in this demo. We're going to talk about how we made that work with the geometry from Unreal Engine, and then we're going to show you some code and some samples. So what is Zorah? Well, this is what the Zorah demo looks like. This is just kind of the opening intro screen for it. It's a sort of a fantastic demo that our art team put together for our Blackwell launch back in January. And what were our technical objectives, right? So we really wanted to showcase something that was truly next generation, because why do we want to show you something that you've already seen before? Also, we wanted to build on a world-leading engine. I'll talk a little bit about that later on, about why we thought that was a sort of an important aspect of this. And then we want to show off the Blackwell hardware because, hey, we're NVIDIA. We like to sell hardware. But at the end of the day, all the features that we're going to talk about today better on Blackwell. So, it doesn't limit you to the latest hardware. So here's a quick demo. Three. So really happy about how the artwork turned out to sort of show off these technologies we're going to talk about. So what are we doing when we're talking about next generation tech? Well, we really want a complex, fully dynamic lighting environment, and for us that meant that path tracing was really going to be the gold standard. Additionally, we had 3,500 lights or over 3,500 lights at different points during the project. Don't quote me on what the final number was. The artist changed things back and forth a little bit. But also we had massively detailed artwork. Specifically, the geometry is in the hundreds of millions of triangles. I think maybe the final count was over 800 million triangles. Adam will talk about that a little bit later. But also the shaders and the textures were extremely complex. This isn't just about like throwing a whole bunch of geometry at it. It's like, what do we need to do to produce some really great looking content? So I mentioned, using a widely used engine, and importantly also one that has available source code such that we can release a branch and show you what we did so that you can understand and see how this would work in an engine. And additionally, it's an engine that is shipping like dozens and dozens of titles. So it's a very ubiquitously used engine, and therefore it is something that you are likely to understand or be using in your own stuff. So path tracing, well, this is really the gold standard for rendering today, for very complex rendering. It supports all these global interactions. It supports arbitrary light counts, complex materials, complex light types. But importantly, naive path tracing can be quite expensive because we have to have shadow rays to handle our direct lighting. We have to have rays for computing these indirect interactions that path tracing supports, and then we have to do recursive rays to light these indirect interactions. So that could be a lot of rays. Importantly, we need to be efficient at this. So that's where ReSTIR comes into play, and that was a foundational technology for us. And Jian's going to talk more about, like, in particular, the ReSTIR PT portion where we improve the indirect interactions. Then finally, DLSS-RR, our DLSS ray reconstruction technology, allows us to denoise things because path tracing, really likes to have a denoiser when we're talking about a real-time context. So geometric detail, you guys have probably heard about Nanite in Unreal 5. But for us, what was going on, what did geometric detail end up meaning? Well, Nanite's fantastic. It allows this, sort of enormous amount of geometry support through a sort of semi-continuous level of detail through these clusters that it swaps out constantly. The unfortunate thing is, we're doing path tracing, so we need to trace rays to do most of our lighting. And Nanite has sort of, minimal or somewhat expensive ray tracing support by default in the engine. And what it offers in the way of ray tracing support is that you can either burn out the current active LODs, which means possibly rebuilding glosses every time that you're sort of changing your geometry because of the fact that you've got this semi-continuous LOD space. And then additionally, you can use the proxy mesh, which is the standard for real-time. And the proxy mesh has, sort of a moderate level of detail, and you can control this artistically. But as we can see with the columns on the left there, on the right there, the left column, shows sort of the full detail, and you see no shadow acting and things like that. If you use the lower res proxy mesh, you're going to have some occlusion artifacts, things like that. You can hide them, but you're still going to lose some geometric detail, and there's going to be some challenges there. So we also had some other bits that we did for Nanite, or for this Zorah project, but we just don't have time to talk about them today. We could do a full day-long course if we wanted to talk about everything we did for Zorah. Linear swept spheres allow us to do better hair, and we intend to talk about that in the future. And then also, we're not going to go into detail on DLSS ray reconstruction. We did some things to help drive it better. With that, I want to hand it over to Jian, who's going to tell you about what we did for path trace light transport in the engine.
Thank you, Evan. Next, let's talk about light transportation, the path tracing light transportation in Zorah. So let's begin with some of the fancy images produced on NVIDIA RTX branch with the Zorah content. As we can see from this image, the lighting here adds up really quite well. Everything is real time. And this is another scene. We call it greenhouse. As we can see some real-time captured color bleeding due to the strong direct illumination on the door here, which is super cool. This is our own modified version of Smonza. We can see the GI signal after 2 mirror bounces. This is super cool, but also very challenging. Speaking of the challenges, we have quite a lot of them in this project. The demo features up to hundreds of millions of triangles in the scene. With this level of geometry complexity, our artists don't want to compromise in terms of material complexity either, as we can imagine that this will actually later introduce some shader divergence problem during GI evaluation. There's also thousands of light sources in the scene. As a matter of fact, in Zorah, we have a few thousand light sources here in the scene, each of which needs to cast shadow. And just because we have this many number of lights in the scene, it doesn't mean that our lighting artists will tend to use the direct illumination signal to lit up the scene. As a matter of fact, a significant proportion of the scene is only lit by indirect lighting. And there's also the mirror problem that we just visited. Last but not least, we need to produce something that is somewhat better than Lumen. Otherwise, it would make very little sense for us to introduce our own tech in the first place. So ReSTIR. ReSTIR is the theoretical foundation of our answer to the light transportation problem in Zorah. We use different variants of ReSTIR in this project. There's ReSTIR DI, which we use to approximate the direct illumination signal. There's also ReSTIR PT, a more advanced variant for ReSTIR GI. We used it to approximate the GI signal. ReSTIR stands for Reservoir-Based Spatial Temporal Important Resampling. It is a method that we can use to improve sample quality by reusing existing samples rather than creating new ones every time. It offers exponential growth in terms of sample quality, but only at linear cost. The method can also be applied to many other generic Monte Carlo problems that is not computer graphics specific. A typical structure of ReSTIR implementation looks like this. It starts with the initial sample pass. First of all, we generate a sample based on some PDF. Then we pack the sample and PDF together in the data structure we call reservoir. Along with last frame's reservoir, we merge them together with resample important sampling in this pass called temporal resampling. The output reservoir is going to be further merged with its neighbor pixels reservoir in the spatial resampling pass. And then finally, we feed the reservoir to the sample evaluation pass, where we do the Monte Carlo evaluation at the end of the day. And due to the time limitation, we won't have time to go through all of the details in ReSTIR. For further detail, please check out this presentation called A Gentle Introduction to ReSTIR. This is the level of noise that we get with only initial sample generation pass. As we can see something going on here, but not everything is super clear. With temporal resampling, things get clear now. And with spatial and temporal resampling together, which is ReSTIR, we got the signal is a whole lot better now. It's still noisy. And at the end of the day, we apply ray reconstruction. We have this nice image that we can finally show to the user. By the way, this particular shot from this camera angle, there's no direct lighting here. There's only sky lighting and also indirect lighting. To fully understand different variants of ReSTIR, it is very important to figure out what the concept of the initial sample is in the initial sample generation pass. So let's go through different variants of ReSTIR. First of all, let's take a look at ReSTIR DI, whose job is to approximate the direct illumination signal in scenes with many lights. Its initial sample concept is quite simple. It's just a location on the light source. During resampling, we simply make the reconnection between what's in the G buffer with the sample itself. This, of course, is a simplified explanation of how ReSTIR DI works. ReSTIR GI is more complicated as it solves a more complicated problem, which is the global illumination problem. Its initial sample now is a path tree rather than a location. The path tree concept is a combination of all paths of different depths. Here, we exclude the path that counts the direct illumination depths because it's already counted in the ReSTIR DI. And we also have this concept called reconnection vertex. Reconnection vertex in ReSTIR, we hard-coded to be X2. So during the reuse, we simply make connection between what's in the G buffer, which is Y1, with X2, the reconnection vertex here. We won't shoot further rays after X2 during the resampling here because we just assume that the sample already drawn by the path X is a good signal for us. And this is essentially where ReSTIR gets its power from. However, in some corner cases, as we can imagine, ReSTIR may fail. Imagine we're looking at a mirror. What happens here is that the BRDF at Y1 may be a poor fit with the reconnection from Y1 to X2. Because when we make the reconnection, we don't value the BRDF. So we're exposed with a risk that with such a mismatch. When such a mismatch happens, we will actually lose some efficiency of the resampling here. Hence, ReSTIR GI will boil down to the standard path tracer. So ReSTIR PT solves the same global illumination problem by avoiding the corner case that we just mentioned. Its initial sample now is just one single pass resample from the path tree. As we know, resampling important sampling is a gray gate machine. That said, passing one pass resample from the whole path tree is sort of equivalent to pass the path tree as a whole in terms of sample quality. It's exactly because we simplify this concept that it actually allows us to defer the reconnection vertex setup in this case. So we can set it to X2, X3, or even further bounces. This offers us the flexibility to apply some conditions for reconnection vertex setup. In Zorah, we have two conditions. The reconnection vertex and the previous vertex, they have to be both rough enough. And also they have to be further away from each other so that we can avoid geometry singularity here. In this case, we can see X2 cannot be the reconnection vertex because X1 is fairly smooth. Well, let's assume X2 and X3 are rough enough. In this case, we can indeed set X3 to be the reconnection vertex. Let's just assume so. And during resampling, we apply an algorithm called hybrid shift mapping. First of all, we need to reconstruct a path. We call it offset path, which is represented by the purple path here. And there's also a concept called the prefix path. In short, it is the subpath before the reconnection vertex in the sample to be reused. In this particular case, we're talking about from the camera to X1 to X2. We would like to produce an offset path that is somewhat similar to the prefix path. In order to achieve so, we decided to reuse the random number that we used to generate a prefix path in the first place. And we know X3 is rough. We also know X2 is rough. So because the offset path is similar to the prefix path, so there's a good chance Y2 is rough as well. Connecting to rough vertexes actually is going to result in good resampling power here. And also we can notice this continuation rate here at Y1 matches with the BRDF quite well. This is essentially how ReSTIR PT improves the performance where ReSTIR GI fails. And next, I'd like to show you guys this image that's Zorah content running with Lumen GI and Lumen reflection. First of all, as we can notice that this whole image is literally lit only by indirect lighting, which is pretty amazing. But just because it's good signal doesn't mean that there's no room for improvement. As a matter of fact, if you take a look at the left side of the image, there's some geometry that lacks occlusion there. And there's also GI signal in the mirror that is somewhat darker than what we see in the primary visibility. So those are something that we could possibly improve with ReSTIR PT. First of all, ReSTIR PT captured the occlusion behind the detailed geometry really quite well. And the GI signal in the mirror is almost comparable with what we see in the primary visibility. This is the biggest improvement that ReSTIR PT brings on the table. Next, I'd like to talk about optimization in ReSTIR PT. This is what we got before we had the optimization. We hit about 26 milliseconds for the initial pass and the ReSTIR PT pass together. Initial pass takes about 20 milliseconds, somewhere around there. And ReSTIR PT, which is the combination of the temporal spatial resampling, costs about 5.4 milliseconds. Here, we're not counting the sample evaluation pass because it's mostly irrelevant to our optimization. It's also very cheap. We'll mention it at the end of the day. So the data is measured on a 1080p buffer before DLSS upscaling, and this is measured with a 1590. The first low-hanging fruit we applied is called quad-arrest ReSTIR. Like many other game engines, we allow quad-arrest GI by assuming diffuse GI is mostly low-frequency signal. We run ReSTIR at quad-arrest, and then we stochastically pick one pixel among the 2x2 pixel quads in the full-res buffer. With the pixel picked, we then copy over the Monte Carlo evaluation of the GI signal from the quad-arrest buffer here. And one detail that is worth mentioning is we need to multiply the Monte Carlo evaluation by 4 because the other 3 pixels won't have the GI signal. This is essentially just to divide the PDF of picking that pixel in the first place. After composition, then we can feed the data to ray reconstruction, which does its magic, not only the denoising, but also upscaling here. And then we finally have this nice image, which is 4K. With this optimization, we cut the cost by almost 4 times for our initial sample pass, which runs the path tracer. And then we got another 3-time performance gain for the temporal spatial resampling. The next optimization I'd like to talk about is called wall-based Russian roulette. As we know, long-tail thread is actually particularly bad for GPU performance due to how GPU works. And it's somewhat inevitable due to how stochastic a Monte Carlo path tracer is. Russian roulette is just one example of many. So in Zorah, we decided to reject things in Russian roulette a whole lot more aggressive than before when we found out that the active number of threads in the WAP is lower than 30%. With this, without introducing any bias, we're gaining about 1 millisecond in the initial pass. Last year, we mentioned we load the Lumen surface card data for indirect lighting for the last bounce. And this is to avoid some darkening bias if the contribution of longer bounce is totally ignored. Here, Lumen surface card is just a form of the irradiance cache. In some other engine, it could be something else. However, this year, we made one key observation, that is, after a diffuse bounce, we have more tolerance against accuracy loss here. Rather than reading Lumen surface card at the last bounce, we choose to read the Lumen surface card immediately after a diffuse bounce. This allows us to save quite some budget here. And what we really ended up doing in Zorah is not only reading the indirect illumination signal at the bound immediately after diffuse bounce, we read the direct illumination signal as well. This allows us to save one more visibility rate along with its NE sampling as well. So with this optimization, we got about twice performance gain here in the initial pass. The next thing I'd like to talk about is how we reduce shader divergence. Earlier in the presentation, I mentioned there's a lot of material in the scene, which is going to introduce some shader divergence problem. Without solving this issue, it could tank our performance. Luckily enough, NVIDIA offers a nice feature called shader execution or ordering since the 40 series. So how does it work? In between we find the intersection and execute the heat group shader, we have a chance to throw all the threads to the SER engine. What comes in the SER engine at the beginning could be arbitrarily ordered. What comes out of the SER engine will be sorted based on the intersection information and also some of the custom bits provided by the developer. This is how we achieve much better walk coherence in the path tracer. It offers quite some performance gain. And there's one more optimization I'd like to mention. That is the inline continuation rate. After a diffuse bounce, again, by making the same assumption that we have more tolerance against accuracy loss, rather than shooting a regular array, we decided to shoot an inline array here because the inline array doesn't need to execute a heat group shader. That's that we're getting rid of the execution divergency in the first place by shooting an inline array here. But there's a catch here. If the scene is present with a lot of ultra cut material, this will tend to overcast. But this didn't really turn out to be a problem in our project, thanks to the Mega Geo work that the team has been working on. So with SER optimized version, we cut the cost by more than twice here. And this is totally orthogonal to all of the mathematics stuff we did. This is the inline continuation rate. We got another 10% on top of the already optimized version of the path tracer. So with all these optimizations, now we're hitting somewhere around 2.7 milliseconds for the whole thing. Given that we solved the indirect lighting for both of the diffuse and the specular bounces here, this is not a bad performance at all. So last, I'd like to show some data comparing with Lumen. This is with Lumen, the same content, same camera angle. It takes about 6.6 milliseconds for everything. Now we can see how performant ReSTIR PT could be, right? And before we move forward, I'd like to point out a few details here. First of all, it wasn't our priority for our artists to adjust the parameter for Lumen. There might be more performance if we could have just adjust the parameter a little bit more. And second, ReSTIR PT produces something that is noisy, while Lumen doesn't. So we should have counted the cost of the denoiser in this comparison, which we didn't. We didn't count the cost because the denoiser is also responsible for denoising the DI signal. So it's not totally fair to add denoiser cost here in this comparison either. So what I'm trying to say here is that there's no good way to make the comparison between the two tech in terms of performance due to how they're structured in the frame. However, I'm still listing the number here just to give you guys some sense that just because of a path tracer in ReSTIR PT implementation, it doesn't mean it has to be very expensive. As a matter of fact, it can be very performant with a highly optimized implementation like the one we have within the NVIDIA RTX branch. Next, I'd like to hand it over to my peer Adam, who's going to talk about ray tracing Nanite.
All right. Thanks, Giant. All right, so we're going to talk about ray tracing Nanite with RTX Mega Geometry. So like Evan said at the top, Nanite introduced several important elements to the Unreal game engine. Did I just lose audio? Okay. First is the clustering of geometry in a hierarchy. That gives us the ability to have semi-continuous geometric LOD that is really visually continuous, and then the streaming in and out to virtualize that geometry. So the really cool part about this is that the clusters are dynamically selected based on the camera's view, and that gives us the ability to adjust geometric detail on the fly and finally eliminate the dreaded LOD pop that we've had for so long. And this works really great with rasterization, but ray tracing APIs really weren't designed with this kind of system in mind. And that's because geometry in ray tracing is represented through a bottom level acceleration structure, or BLAS. And changing even a single cluster in a BLAS means we'll have to do a complete rebuild of that BLAS. And if we're using a lot of Nanite geometry in a scene, that means we're going to rebuild all of that geometry, which means we may rebuild all the geometry of the entire scene every frame, which is just not going to fly. It's going to be too expensive. So what do we do? Epic's solution to this is to have Nanite itself generate low complexity proxy meshes, as they call it, for use in ray tracing. And typically these meshes are about 5% the detail of the full mesh. This is adjustable in the editor, of course, but this is the default setting. And the BLASs built here are built once and they never change. And it looks something like this. So now we have a problem. What the geometry that's used in rasterization and the geometry that's used in ray tracing are now different. And this creates quite a few visual issues. Self-intersections, like Evan showed in the image at the beginning, incorrect shadows from proxy meshes, so the actual mesh itself is the wrong shape, so it will cast the wrong shadow. And then in reflections, for instance, you could have low geometric complexity of the meshes that are being reflected. So how do we work around this? Currently in the engine, for self-intersection, the workaround is to use large bias values for things like shadows. The problem with this workaround is that contact shadows will be lost. For incorrect shadows, where you have the wrong shadow shape, Epic built a system called virtual shadow maps, or VSM, which is very good, but it has a limited ability, like many shadow mapping algorithms, to reproduce penumbra accurately. And then finally, for reflections, you could always fall back to SSR, but that comes with a whole host of visual artifacts and issues to deal with. You could also ask your artists to tweak the geometric detail of the proxies to boost it up, but that adds a lot of manual artist work. It takes more memory, and it's just overall difficult. So here are some visual examples of everything I just talked about. This is the greenhouse scene in Zorah. And if you look here, you'll see an example of the incorrect shadows. So this is a very faceted shadow that isn't representative of the actual geometry. And if you look here, you'll see some very large triangles. There is a tree off screen on the right, and that tree, its proxy mesh for the leaves are these large triangles. If you look in the reflection, you'll also see those large triangles again. And then on the left, this might be hard for some of you to see here, but there are quite a few self-intersections on this bush, so false shadows that aren't correct. And if we turn on Mega Geo, I'll flip back and forth, all of those issues go away. So our shadow, our sort of incorrect shadow, is now nice and representative of the smooth geometry that our team made. Our leaves look like leaves in both shadows and reflections, and those false intersections or false shadows on the bush on the left are now gone. So what is mega geometry? Ultimately, it boils down to enhanced acceleration structures. So there are two main features. The first is called partition TLAS, and this modifies the top level of the acceleration structure, and it makes it so you can avoid rebuilding the entire top level every frame. And then there's the clustered BLAS. This is for the bottom level, and it gives us the ability to add a new type of acceleration structure called the clustered BLAS, or clustered level acceleration structure. I'll talk about that a little bit more next. So the benefits of these enhanced acceleration structures are that we can build them in large batches now with minimal CPU overhead. So it's an indirect API. And the major benefit of this is that building acceleration structures, and hundreds or thousands of them, is now very fast. We can build BLASs up to 100 times faster than with a vanilla DXR. This is available through NVAPI right now. It works in D3D and Vulkan, and all RTX GPUs, so back to Turing, are supported here. We're going to have a talk later today at 5 p.m. where we'll talk about the Mega Geo API. So if you're interested in more details, make sure you come and hear that talk. Okay, so now I'm going to talk about how we implemented Mega Geometry in Unreal 5 in our NVRTX branch. And there are a lot of steps here. So I'm going to walk through it one at a time and try and zoom in on each one, and I'll talk a little bit about each step. So the first thing is Nanite itself in the engine. it streams geometry in and out on the GPU asynchronously. And it will upload and install Nanite pages onto the GPU as it does its work. These Nanite pages contain clusters of triangles. And for Mega Geometry, our goal is to turn those clusters of triangles into the CLASs, or cluster level acceleration structures. And then we'll use those to assemble BLASs that will be ray traced. So we want to keep track of Nanite page IDs as they're installed to and evicted from the GPU so that we can stay in sync with the Nanite streamer. All right, next, the engine will create the ray tracing scene, and it'll iterate over all the instances of objects in the scene. And we snuck in some code to make sure that we're keeping track of how many Nanite mesh instances before any culling happens are in the scene. And then on the GPU, the top-level acceleration structure instance buffer will be created and will perform GPU culling. And again, snuck in some code to track and store the number of Nanite mesh instances that pass the culling on the GPU, so we can store metadata about those for later. All right, one more CPU side task before we get going. We need to make sure we allocate the right amount of GPU memory. So since Mega Geometry as an API is fully indirect, once it starts executing on the GPU, it needs to have all the memory that it's going to use before that happens. So we got to make sure that we allocate that up front. And we can do this using the ray tracing scene and using an incredibly easy to remember and very short function name that is part of the Mega Geometry API. We also use we extensively use reserved resources throughout our implementation so that we can resize buffers without having to reallocate and copy future or previous data into them. And this helps with CPU side stutter. All right, so now we're to the fun part, Nanite hierarchy traversal. So we want to select the clusters for each Nanite mesh instance, which ultimately is a clustered BLAS. And this is where we're going to select our LOD, our geometric LOD dynamically. This is the same thing that Nanite does in rasterization, but we're going to customize that traversal process a little bit and change the culling logic to be specific for ray tracing. One thing we're keeping the same, though, is that we're going to match the clusters that are selected in Frustum with the rasterizer. And critically, this makes it so we can eliminate that geometry mismatch. So we'll keep occluded clusters, clusters behind objects, and clusters outside the Frustum, but we're going to match them in the Frustum. So we'll output a bunch of data about these clusters and keep a list about them for use a little bit later. So we haven't built any CLAS yet, but on a previous frame, we may have. And we keep these in a big array on the GPU cached. And we need to keep in sync with the Nanite streamer as it moves things in and out of memory every frame. And an important aspect of this is evicting CLASs that are no longer used and compacting or defragmenting that CLAS array on the GPU to make sure we're not using more memory than is necessary. And fortunately, the MegaGeo API provides us a nice move operation so that we can move CLASs around to make this happen. And this process is essential to make sure we just don't fill up the GPU with a bunch of CLASs. All right, next, now we're on to the building part. So we want to take Nanite pages, decode them, and get the cluster geometry. We'll store the indices and vertices and geometry indices of those clusters. And this whole process is a multi-step process handled in compute shaders. And at the bottom of the slide here, you'll see some links to some shaders. We're releasing the code in NVRTX. It's actually already up now. And so these are the shaders you can go to see exactly what happens in this process. It's too much to talk about here, and you might fall asleep. So you can look at it in your own time. But the big takeaway of this process is that we want to prepare indirect arguments and descriptor structs for the CLAS builder to consume. So we hand all that to the CLAS builder, and it builds all the CLASs at once. Life is great. It stores those in a buffer. For the Unreal implementation, we have a very small temp buffer that we can know the size of up front And it would be something like this. And then we'll run a few compute shaders for bookkeeping. Again, I've put them at the bottom so you can check them out. These will then append the newly built CLASs into that large array that I was talking about earlier that gets defragged. Okay, so now that we have our CLASs built, we want to get to the end and build our BLASs. So to do this, we need to assemble a list of CLAS virtual addresses for each BLAS. So before, during that Nanite traversal step, we made a list of CLASs that were selected. This is where that list comes back into context. So we want to process that list and ultimately end up here, where we have a BLAS pointing to the CLASs that it is going to use that have been selected for its level of detail. Again, this is a multi-step process. It's all handled in parallel in compute shaders. And just like before, its goal ultimately is to prepare indirect arguments and descriptor structs to hand this time to the BLAS builder. So once that's done, our clustered BLAS are all built. They're dropped in an array on the GPU. And we have one more step to do, which is we need to update the BLAS pointers of the TLAS instance descriptors. So if we don't do this, Unreal will use the proxy meshes, proxy mesh BLASs for ray tracing. So we'll want to update those to point to the new ones, the new clustered BLASs that we just built. And then finally we can build the TLAS and do some ray tracing. And so did we do it? Is RTX on? Yes. So one of the things that I was really excited about doing for Zorah and this project was tracing primary rays. So what you're looking at in this image does not use rasterization for the G-buffer. It ray traces primary rays against all the Nanite content. So if I give you a visualization of that, these are the intersected triangles by those primary rays with Mega Geometry turned on. If we were to use the proxies instead, the proxy meshes, it would look something more like this. So you can see the amount of geometry traced is very different. Okay, in addition to primary rays, of course, shadows, very important. And I'll start with contact shadows. Here's a visualization of the Nanite proxy mesh normals, surface normals. And this is it with Mega Geo turned on. So if you're in the back, this may be hard to see, but the high frequency detail in the Mega Geometry is substantially different. Here's the lit image with the proxy mesh, and here it is with Mega Geo turned on. And so hopefully, when you watch this back in the recording, you'll see the contact shadows are substantially different in that with the proxies, they don't exist at all in many places, and they come back with Mega Geo. In addition to contact shadows, indirect soft shadows or ambient occlusion, we can completely transform when we have high fidelity correct geometry in the BVH. So here's another example in Zorah. This is the proxy mesh version, and this is Mega Geometry. So the vines going up on the side here, the occlusion detail is completely different when you have the correct geometry in there. All right, reflections. So here we are looking in a mirror in Zorah, and in this mirror, there are a few spots where the proxy mesh just can't decide where it wants to put the most geometry. And as a result, sometimes the proxy mesh doesn't represent our artist's intent. And here it is with Mega Geo turned on. So we can produce the correct, accurate LOD, even for something that's completely off camera and shown in a reflection. Here's a more subtle example, but still important, where we have a metal grate and the proxy mesh is more faceted and doesn't have the geometry that we would want. It's also static, but with Mega Geometry, we can make it full quality and dynamically allotted. And one more example here this is a foliage example where with the proxy, sometimes the Nanite encoder has to decimate the proxy so much that it actually is gone. And here's an example where the foliage isn't represented by proxies in some cases, or it's a very low faceted proxy. All right, and of course, GI. That's what Jayan already talked about. So ReSTIR GI and ReSTIR PT, very great use cases for Mega Geometry. When you're going to spend compute power and time bouncing rays around, you want to make sure they're bouncing off of the right stuff. So performance and memory. Clustered BLAS build performance, you can expect around 1 million CLAS per millisecond on Blackwell on a 5090 when you're building your clustered BLASs. We're continuing to optimize and improve that in the driver. And then acceleration structure memory, I mentioned several times we're caching CLASs in GPU memory. The CLASs and the BLASs will be 30% less, will take up 30% less memory on Blackwell than prior architectures. All right, so massive geometric complexity and dynamic LOD have arrived for ray tracing with Mega Geometry, and we're really just getting started here. We still need to support a variety of things in NVRTX and UE5, including world position offset, skinned nanite meshes, and nanite tessellation displacement are a really great use case for Mega Geometry's CLAS templates feature, which I haven't talked about here, but if you go to the talk this afternoon, you'll learn a lot more about it and its use in Alan Wake 2. One more note, NVRTX 5.4, which includes the implementation of what you just saw, is experimental. It's not quite yet ready for AAA games to ship out with it yet. We're working on those limitations, and that could be a whole talk in and of itself. But just keep this in mind. Pull the code, experiment with it, play with it, but don't expect it to be perfect just yet. So like I said, code is available now. If you go to this QR code or this link, you can pull it. It's part of our NVRTX branch. It's, like I said, it's got both features. It's got clustered BLAS and partition TLAS. Even though I didn't talk about partition TLAS much today, it is in there. All the code for both features are surrounded by these defines. So if you're looking for how did they change the engine, what's the new stuff, search for these defines and you'll find everything. Also, if you just want to use one of the features and not the other, you can compile out the features completely if you like. We also have content samples coming soon to the Unreal Engine Marketplace. These are made by our artists and were shown in the video at the top. We have a greenhouse sample, a throne room, which is shown here. I love this sample because of the incredible sculpted detail. And then a sort of Sponza-inspired scene as well that Jayan showed. Tools. Tools are important, and you can use tools to learn. Insight Graphics 25.2 is available now, and it has initial support for Mega Geometry and D3D12. It's a great way for you to pull the code, pull the samples, run them, and then see a breakdown of the passes, the resources, and the shaders as they execute. So you don't have to just stare at the shader code. You can download the latest version here. And I just want to do a quick shout out to a lot of folks. There's a huge team of people that worked on Zorah across engineering and art and different parts of the organization. You don't do this with 3 people. We get to be up here and present, but it was a lot of effort from a lot of great people. So this is the engineering side, and this is our Lightspeed art team. Like John mentioned this morning, we have an in-house game studio, and they create the incredible art assets that you've seen on screen and that you'll be able to download from the marketplace. And that's it. Any questions?
Just one reminder.
Is it not on? Oh, before you all run away, a reminder to fill out your evaluations, please.
Hello. Okay.
Hey.
Hi. So I have a question. Can you elaborate on how you select clusters to build the BLAS and CLAS? because in Nanite, traditionally you use the Frustum and you have an error metric that is basically targeting less than a pixel error. But in ray tracing, you don't really know what you are going to hit with the rays. So how does that work?
Yep, great question. So the question is, I'm going to repeat it since we've got a lot of people moving around. To elaborate on how we select clusters in ray tracing compared to what Nanite does for rasterization, and the heuristic that Nanite uses. So Nanite's heuristic is to try and target essentially one triangle per pixel. And in ray tracing, that is less relevant for a few reasons, because you have things behind you and things in reflections that you might want a lot of detail on, but you might not. So for the primary view, the heuristic is exactly the same. The shader simplifies and cuts out some of the stuff that the Nanite raster's traversal does. We don't do two-pass occlusion, culling, and it's mostly just a simplified version of the same heuristic. For off-screen stuff, for anything out of Frustum, we run the same heuristic, but then we have a variable where you can scale the LOD. So essentially limit the depth at which the traversal can go in the tree so that the geometric detail that's selected, the clusters that are selected, is configurable. So for
Is it like distance based or that's there's the some sort. I think the mic is cut.
Is it like a distance-based metric from the camera?
Yes, so the heuristic itself is distance-based.
Yeah.
And so essentially what I do is I find the vector of sort of dominance, use that to run Nanite's existing heuristic, and then use the scaler to scale that down. So depending on where you are behind the camera, it'll find that dominant vector and then run Nanite's heuristic, and then we can scale it from there. And the scaling, particularly for things that are far away and off screen, you can be somewhat aggressive. Yeah.
Okay, thank you.
Yes, I had a question for the reservoir sampling or importance sampling that was talked about sort of in the beginning. So when, if I remember correctly, we use sort of past samples to influence the generation of like future samples, to save time and to be more efficient performance-wise. How do you kind of account for that in terms of like the PDF and like proper weighting of samples?
Sorry. Can you repeat that question again?
Yeah. So when we use like past samples to generate, or when you use like past sample generation to more efficiently generate like future samples, how do we account for that in like our sample weighting and like our PDFs?
Okay. So let me repeat the question. Your question is, when we reuse the sample from the past, like the past sample, how do we reevaluate the sample based on how important the sample is, right?
Yes.
So I guess the question really is like in terms of ReSTIR or the language resample importance sampling, what is the target function for the pass? Is that what your question is?
Yeah, pretty much.
Yeah. So in a nutshell, there's a term called target function. When we do the reuse in resample importance sampling, a target function essentially defines how important or how important you want to value the sample. So such a target function could literally be anything. It doesn't need to be normalized. It just can be a function. Normally in ReSTIR, in ReSTIR DI, we use in the original paper, we use the unshadowed light transportation of the render equation. And we don't use the shadow ray because just to try to save some performance there. But for ReSTIR GI and ReSTIR PT, we just use the whole render equation as just one pass, of course. We use that as a target function. That's how we value how important a pass sample is. Does that answer your question?
I think I'm still a little bit confused. So like for the importance sampling, right? Yeah, when we do our importance sampling, how do we sort of, because if we have like past samples influence onto like future samples, how do how are we specifically accounting for that, or does that not matter in the end?
Yeah. So how things temporally work out in ReSTIR is that you maintain this this M value that is tied to the amount of temporal history that you got in the reservoir, and that tends to we cap that, right? So the more that reservoir has been around, the more important it becomes with respect to its importance sampling. So you're weighted by how confident you are in the temporal history that you've accumulated into that sample. That's basically one of the factors that goes into the computation of the PDF for selecting the new sample versus the temporal sample. And then also we do keep a historical light list and things like that. So when you're using DI, you're doing the reevaluations of the lights, you're going to evaluate against like how the light changed for doing some of that resampling stuff. Does that help you out?
Yeah, that definitely helps.
And there's one detail I'd like to mention that you just mentioned, like how do we reevaluate the past sample, right? So with ReSTIR, we not only just reevaluate the past sample, we also we also borrow the reservoir from this frame's neighbor pixel as well. That's not past frame, that's not past data. It's just like we got, let's say you find a small kernel. Within the kernel, you draw a few pixel samples and you check what those samples are, what the reservoir for those samples are, and then try to merge them together with the resampling and sampling together. So it's not just past sample, there's current sample going on as well.
Okay, yeah, that definitely makes a lot more sense. Also, where can I access the paper for this method?
If we have time, feel free to go for it, because you got two person.
Yeah. How about you come over and we can talk to you more?
A great resource is to just Google a gentle introduction to ReSTIR. It's a SIGGRAPH course from last year that you can take a look at, or the year before.
Okay, perfect. Thank you.
Hello, guys. Thanks for the presentation. So about ReSTIR, I saw that you had some incredible advancements. The question is about extreme light change scenarios, if it's responsible, because this is a long-known issue. And the second one is about, like, at least on the example, I saw that you have like perfect mirrors, but how things behave when you have like mixed faultness.
So for the first question, let me just repeat it. So your question is that how are we going to deal with the case when we have standard changes of light sources, right? The light is lighting up. It depends on how dramatic the change is, right? If we're like totally shifting the camera to a totally different position, every pixel, the whole reservoir of history is just totally invalid, like totally not valuable for us, right? In that case, we'll just throw away all the history there. But in some cases, like we rely on the target function, which will give us some indication of how important this signal is, how important do we want this signal to be, and that's how we evaluate. I mean, normally in sudden changes of light sources, the target function should be lower for the temporal history. And there are some other tricks like we did. For example, like we're gonna check the history, some of the heuristic for normal or depths, that sort of information. If we find like dramatic changes in such a signal, we will tend to reject those reservoirs regardless what the target function is.
Okay. Yeah, I was going to add, and because we're tracking the light history, we reevaluate against, the light has moved. We will test, like, is it still visible? Things like that, right? So, if suddenly that light got entirely shadowed because something moved in front of it, those are going to, run their PDF down to 0, and they're not going to get reselected. And we're going to grab the new initial sample, which has the up-to-date information, things like that.
What is your second question? Do you mind repeating?
Oh yes, with like mixed faultness for like
Mirrors versus diffuse.
I mean, for mirror pixel, our strategy is to apply this ReSTIR algorithm. I mean, the real algorithm is actually a lot more complicated than what I just explained because we have the time limitations here. So in short, we apply this algorithm called hybrid shift mapping. And the hybrid shift mapping essentially is just before the reconnection depths, we start to reuse all the random number. After the reconnection, we reuse the past in the primary sample space. And there's also some complication caused by the shift mapping because we need to convert the path from whatever the domain is drawn from to our own domain. And there's also that complication as well. But with the hybrid shift mapping, this is actually our trick how we solved the mirror problem. It's going to enhance the signal within the mirror a lot better than ReSTIR GI.
All right, perfect. Thank you.
Thanks.
Hi guys, had a question with ReSTIR and ray reconstruction. So I've been working with both technologies for a while, and I came up on a render with a ReSTIR implementation that was, I believe, based on the original paper. And then upon implementation of ray reconstruction, we're noticing like patterns build up, especially in unlit areas, and simply disabling spatial and temporal reuse completely fixes these patterns, and instead just using importance sampling for local lights, and it works way better without any reuse. So you guys have any solution for this if we are to use ReSTIR?
Yeah, so the question was that you've personally implemented some ReSTIR stuff based on the original paper and have recently worked with applying ray reconstruction, and you have noticed in certain cases some sort of like pattern reinforcement and things occurring with the ray reconstruction, but you're seeing better results if you switch to pure Monte Carlo.
Yeah.
So what we have done here is we have broadened out like some of our temporal history radius and stuff like that to ensure that we maintain a more stochastic sort of result. Like we are intentionally keeping a little bit more noise in the signal here. We're still getting a strengthening of the signal, but we're intentionally keeping a little bit more noise to help ensure that ray reconstruction operates a bit better, because it does operate. If you get too much correlation with a denoiser, sometimes the denoiser can overfixate on the correlation. And what we're doing is making sure that we have better stochastic sort of values in there to ensure that the correlation isn't showing through to the denoiser. Does that solve you?
Yeah, so basically it's because the original paper didn't have that, and the implementation just was too, there was too much correlation in that, so too much reuse and not enough noise, different noise patterns, and DLSS was like kind of finding these patterns and applying it as like a texture, right?
DLSS doesn't like particular patternized stuff, right?
Yeah.
So I have a question. So what is your version of DLSS?
Well, both DLSS 3 and DLSS 4 have that same pattern.
Have you tried the transformer version DLSS?
Yes, that's with DLSS 4, yes, with reconstruction, with the new, was that J algorithm, I believe, the new one.
Yeah, that's the one.
So they both have that same.
Ultimately, it likes high frequencies.
Yeah.
Because if you have low frequencies, you'll get more correlation.
Yeah.
And it's a pattern matching machine.
Yeah.
And so it'll be like, you want this pattern. But if you sprinkle in those higher frequencies, it won't do that.
Yeah, so
that's what you're...
basically adding more noise to it actually fixes the issue.
It improves the result, yes.
Okay, yeah. Improves it. Okay.
The thing is, all of our implementation regarding to light transportation that we mentioned in this presentation is fully public online. So you can go to GitHub on the NVRTX branch with a compatible account. You should be able to access all the source code. All of our implementation is there, so you can check how we reproduce, how we solve the problem. And because as Adam mentioned, that the Zorah the content will be available on the market, so you will be able to run the content with the source code. What's this?
So you can essentially check, see how your frequencies match up. I'm getting a look from the back. Are we at time? Okay, we're at time. So we can answer your questions afterwards. Just come on up and we'll talk. Thank you.